正在连接。已解锁，请取出话筒。解锁，请取出话筒。
Hello, hello. Good morning to everyone. So last time we finished at this examples here, trying to prove that the equation x cubed plus x minus 1 equals 0 has exactly one real root. So what does it mean by one real root? I mean, there's only one solution. So we're going to use continuity of this polynomial function to show that this equation has one real root. But if you realize, what we have done was we identified a interval. Okay? We identify an interval for this polynomial such that at one endpoint it is taking the positive value, and on the other endpoint it's taking a negative value. Okay? So when x equals 0, f0 is minus 1, and then when x equals 1, f1 is, okay, seeing it is continuous, so they must have some point, okay, that pass through y equals. Well, the graph could be something like this. It could pass through twice. I mean, 3 times in this case, or maybe even more. Okay, so our job is to show why there's only one of it. And if you still remember, when we do this, we assume there are two different real roots, and then we reach a contradiction. But anyone realize any problem here? I realize any problem with this argument. Actually, we are not quite done yet. Why? Because what we have shown is just within this 0 to 1 interval, there's only one real root. We have other real roots for x less than 0, for x greater than 1. We have other real roots, meaning can this graph like going down again, having solution? When we have this kind of graph, is it possible? Can we have real root at other x's other than 0 to 1? I think someone mentioned what increasing to me last time. So you want to make sure that this graph can't turn back to this y equals 0 line intersecting the x-axis. Okay, is it possible to show it? Okay, so let's try it. Let's try some algebra here. So if you have x less than 0, okay, what is x cubed? Is it still less than 0? Yeah, okay, so still less than 0. Then what about x cubed plus x plus, minus 1? It is less than 0 plus 0 minus 1, which is minus 1. Okay, so meaning for any x less than 0, fx will be always strictly less than minus 1, which is obviously less than 0. So you never met y equal to 0 again, okay, for all the x's less than 1. So we can do another analysis, right? How about for all the x's greater than 1? So if x greater than 1, what is x cubed? It's also strictly greater than 1. Is everyone fine with this? So if you have like 1.1, you take a cube, what do you get? Do you still get some number greater than 1? Okay. So fx equals to x cubed plus x minus 1 is strictly greater than 1 plus 1 minus 1, which is 1 plus 1 minus 1, 1, which is greater than 0. Okay, so meaning after x greater than 1 or before x less than 0, this graph here wouldn't be intersecting y equals to c. Okay, so we are good. Make sense? Okay, obviously, you can use injectivity. Okay, any question? So we have finished this one. This like with that. Okay. Yeah, question? No? Okay. Yeah, feel free to ask, because I know after the lecture you will come out and ask. So meaning actually you have question, but please ask. Yeah, during the lecture is better because everyone is here, so we could discuss the problem together. Instead of I just telling you, because it's like if I tell you, I need to tell everyone else again. So it's better that we discuss it. Okay. Any question on the previous lecture? Have you tried the homework? Felicia, have you tried the homework that I get? What number? Like those questions that I didn't do in class. Did you try? Yeah, so please try. So if you met any problem, right, you can ask or send in the Moodle, yeah, and then maybe your classmate can help out. Okay, so we will continue a little bit more with mean value theorem, and then we will switch gear again. Okay, so let's recall what is the mean value theorem. Okay, so what's mean value theorem? Let f be continuous on a closed interval and differentiable on the interior point, so open interval from A to B. Then you can find a point within the open interval C inside interval AB such that the derivative at this point here can be realized by the secant that join AFA and BFB. Okay, so how do you remember this theorem here? There's so many words here. Okay, what you should remember here was the picture. Okay, so picture should help you to remember this theorem here. So you have A, B here, right? And then you have some continuous graph. Then you have a secant joining AFA and BFV. Maybe use another color. Actually, for the words. Okay, so if you try and take this line, okay, with the same gradient here, you should be able to find another point that have this gradient of tangent. Tangent. So, for example, for the continuous graph I drew here, there are two of them. Okay, but the theorem here guarantee that there is at least one. So maybe this one C1, C2. Okay, makes sense. Okay, and then we call this ratio here or this gradient here as the mean value. Okay, so far, okay. Okay, so let's remember this theorem and then see how we can find a different question here. All right, so let fx be this cube root of a square on this closed interval here. Show that the conclusion of the mean value theorem fails. And figure out why. Okay, so meaning fail means what? You cannot find a point. Okay, to realize the secant gradient, the gradient of the secant. So let's show that why it fails and then we figure out why. Let's take another page. So let's quickly do it. For example 4.1. Fx. Let's take 2/3 on closed interval minus 8 to 27. And let's just show that why it fell. So to show why it fell, so let's compute what's the secant, the gradient of secant that join the two endpoints. So if we compute this, we'll get something like 1/7. Okay. So I'll try and solve this. Okay, let's see if we can find a point again that solve this. So to do that, also we need to compute what's the derivative of f. Okay, so if we compute what's the derivative of f, then what is it? 2/3 of cube root x. So we want to see where this the derivative equal to 1/7. See, can we solve for it or not? Uh, suppose f prime x equals to 1/7. Okay, so if we suppose this, can we find an x that satisfies this or not? Okay. So if we solve this, what do we get? Here we get 9. Make any mistake or not? So cube root go there. Okay, 7, I think it should go up. So 7 should go up. Okay, so what is this? Is 相似 here? Not? Hi, can you help compute what's this? And you can use calculator. Two thousand. 2000. 2000 and what? Around 24. Oh, is it? Okay. Sorry. Oh, bottom, there's some more. 27. Okay, so can you give the decimal? What's the decimal for this? Give us the decimal. 100. Okay. 62. Okay. 63 or 62? 63. 63. 62. 3 or 2? You 3, yeah? 101. 63. Okay. 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 So 100 is way far from our close interval here. Okay. So you do have this point here, but this point is not in this interval that we consider. So what could be wrong? So what could be wrong here? Okay, so if you still remember just now, we say that f have to be continuous at the closed interval and also differentiable. Okay, so these two conditions here. So what do you think? Which condition could be false? Which condition? Both false or one of them false? If one of them false, which one will false? Continuity? Do you think continuity will be false? This is square of a cube root. So if you square it first, then square is fine, right? So square is continuous. And if both sides are already positive, then cube root should work. Negative works or not? Negative also works actually, right? For cube. Okay, so actually this graph, this function, if you want to show using the limit where it is actually continuous. Okay, so something wrong with differentiability actually, but you should be observed from this formula already. Like, does this fraction here always exist? Where it doesn't exist? Zero. Yeah. Realize that zero is inside your interval that you consider. Zero will go wrong. Okay, does it make sense? Okay, so actually, in fact, it doesn't satisfy the mean value theorem problem. Okay, so in fact, f is not differentiable at x equals to 0. Okay, so to show this, you need to use the limit way. Please don't use the formula way because the formula way is a bit cheating. Without doing the limit, you're not sure why you get that formula actually. Okay, so if you really compute this, if you compute this formula, then what you get is limit of x to infinity of 1 over q of x. Okay, so this guy blow up, okay, go to infinity when x approach to 0. Okay, so this guy doesn't exist. Okay, so you might think that the condition is broken. It's broken. It is broken at the x equals 0. but the thing that you can find is at 100, around 100. So the sufficient condition here is really important, okay, for the theorem to work. Any questions so far for this? Yeah, any question? Okay. Okay. Um, so, so we can try and apply this to real life. So maybe real life problem is really important. Yeah. So suppose that the position of an object at t second is given by the following formula, the polynomial t squared minus t minus 2. Find the average velocity over the interval from time 3 to time 6 seconds. And then find the time when the instantaneous velocity equals to the average velocity. Okay, so there are two concepts here you need to separate. So average velocity is just the final distance minus the initial distance and then divided by the total time. Okay. But instantaneous velocity is the one that we find for the derivative. So this is exactly the secant matching, secant from the endpoint matching to the sum of the gradient inside your tangent line. I mean, tangent lines that that your curve have. Okay. So let's do it one by one then. So what's your average velocity here? So you just take your endpoint and then take their difference divided by the total time. And you should get something like 32. So maybe we could draw this graph, right? This graph I think is not too hard to draw. Maybe it's t minus 2 and then t plus 1. And which is here is minus 1, here is 2. Okay, but we care about the interval from 3 to 6. So it's way back. 3 here, 6 maybe here. Okay, so we just care about this side of it. Okay, so what we do to the average velocity was we take the final distance minus the initial distance for displacement and then divided by the time, which is the gradient of this secant. So we want to ask, is there any other time, okay, that has a tangent line, okay, equal with a gradient equal to this gradient, no? So this is a mean value type of question. So can we use mean value theorem here? Because t squared minus t minus 2 is just some polynomial function. And polynomial function is continuous. Moreover, it is differentiable. Okay, so we can use mean value theorem. So if we want to use a mean value theorem here, we want to find the x's. So let's consider the derivative x prime t, which is equals to 2t minus 1. And then let x prime t equals to 32 over 3. So I think from quick calculation here, you get t equals to 35 over 6. Okay, if you divide it up, I think it's around 5, 6, 5, 8, 8, and then 3, I think 8, 3, 3, 3, 3, 3, 3, 3. Okay, so it's safe in the region of 3 seconds and 6. Okay, so this is the time loop one. Okay, makes sense. So this existence here is guaranteed by the mean value theorem. Yes, question. You find 24 over 3? 24. 24. Is it? Wait, I think I know where go wrong here. So I think, so what I did in my note was 28 plus 4. So actually it's minus 4, is it? So, okay, good, thank you. So here 24, and then here 24. Here 24. Wait, let me see. So 24 plus 3, right? So here's 27. So 27 divided by 6 is 4 point something, right? 4 point, 4.5. Okay, good. Okay, nice. Still in the region of 3. Okay. Yeah. So if you spot any calculation error in my lecture notes, please feel free to uh, inform me. Okay. So far, other more questions? No. Okay. So let's go to the next one. So now I told you that f0 is 3, and I told you that for all x, the gradient at all these points cannot be greater than 5. Use the mean value theorem to find an upper bound for f2. So what's the picture you should appear in your mind here? So you have a f0, maybe 0 here, and then somewhere 2. So I don't know how to study this f2 here. But the point here is at every point fx, the steep, okay, cannot go greater than 5. Okay, you cannot, let's say this is equals to 5 here. So all the other tangent line, right, cannot exit this slanted degree. So you could have gradient like this, I mean tangent line, or you can have tangent line like this, or even negative one is fine. But you cannot have steeper tangent line in the positive direction. Make sense? So this kind of control how much you can increase, right? This control how much you can increase. Make sense? Okay. So, but what should you use here? What should you use here? Since this is listed under mean value theorem, right? We're supposed to be able to find a way to use mean value theorem. But to use mean value theorem, you need continuity or differentiability. Okay. But this question didn't tell you. So let's assume it. Okay, so let's assume it. Okay, supposedly we should assume it. So I think in this question, we should suppose that let's add some additional condition here. Okay, well, okay, I shouldn't say add some conditional condition, but I think from this derivative here, we should infer that this function is actually continuous and differentiable for all x. Okay, so by assumption, actually f is continuous on everything. No, not just continuous. It's actually differentiable. Okay? And differentiable imply continuous. Okay, if you still remember last time the theorem that we introduced. So differentiable is stronger than continuity, or differentiable implies continuity. Okay, so what should we do here? So let's do some little working here. So if we try and make a secant here, so f2 minus f0 over 2. Can we relate this gradient here to some other derivative or not? Mean value theorem says what? There's some point at your graph which have a derivative equal to this gradient of secant. Okay. But this question says what? No matter how you find the derivative, this derivative cannot be greater or equal than 1. Okay. So we will use back engineer on mean value theorem. We know that for OX, f2 minus f0 over 2, okay? I cannot say for OX, right? That exists X. Okay. Actually, this mean value theorem that tell you that this X should live in between 0 and 2, right? Okay. Equals to f prime X, but the question says for OX, okay, this number here cannot be greater or equal to 5. Okay, no matter what. Okay, so this f prime X here is less than or equals to 5. Okay. Okay, maybe I should make this into C so that I want you to know that this X is already fixed. Okay, it's chosen already. Okay, this T is a fixed T. But the f prime X here is for all X. Okay, for all. Okay, then this tells you what? This tells you that f2 is less than or equals to 10 plus f0, okay, which is 10 plus 3, which is 13. Okay, so we found that f2 is less than equals to 13. And the question asks you that what's the upper bound for f2? Upper bound meaning what's the number that's greater or equals to f2? Okay, we found one possibility, which is 13. If you put 14, correct or wrong? You said that the upper bound for f2 is 14. Is it correct or wrong? Can I put 14? Ah, cannot? Why? Why can't I put 14? Sorry? Sorry? Still thinking again. Why? So I already found that f2 is less than or equals to 13. So an upper bound is a number that's greater or equal to f2 if you want to find an upper bound for f2. Can I put 14 or not? Huh? Can I put 14? No? Why? Can I put 14? idea? I proved that F2 is less than or equal to 13. So can I let my upper bound to be 14? Yeah, hello, yeah, online. Okay. Can I put 14? I think there's no calculation to be done here, just that you know what is upper bound is. What's upper bound?
So
Yes.
it means when x equals to the x, the maximum when x is 13 is be its average let's see, average
Average.
the average speed will go up
Go up.
up.
I mean, like, for example, let's say, okay, this inequality said that F2 is less than or equal to 13, right? Maybe F2 is 13. It's just 13. So is 13 still less than 14? So it is an upper bound. Right. So what's the definition of upper bound? Maybe let's talk about definition of upper bound. And upper bound for a number x is a number y such that x is less than or equal to y. That's it. Okay, as long as this number is greater or equal to x, that's fine. You already show that your number is less than or equal to 13. Obviously, 13 is less than or equal to 14. 14 is also less than or equal to 100. So 100 could be an upper bound as well. Make sense? But if you put 12, then it will be wrong. Because 12 is less than or equal to 10. Okay, unless you have another way to prove that, oh, you can shrink down this 13 to 12. Unless you have another way. Otherwise, based on this, you cannot say that 12 is an upper bound. Okay. Does it make sense? Okay. All right. What time is it? Okay, we still have time. Let's continue. All right. There's a very powerful theorem here. It can detect. I mean, it can tell you how to produce a constant function. Okay, so it just says that if f prime x equals 0 for all x in AB, so once we talk about this derivative, right, I think one images you need to form in your mind is the tangent line. Okay, so meaning that at all points, your tangent line is horizontal. Right? Your tangent line is horizontal. So what kind of graph you can have with this horizontal line? Okay, and then this theorem tells you that you can only have one graph, which is constant. Okay, makes sense? Okay, we won't prove this. I will put the proof inside the notes if you want to see. But if not, um, you just understand it. Corollary is if you have two functions that have the same derivative, meaning the way their tangent line slanted is the same, then they are just differ by a constant. And then they are just differ by the okay. So corollary means what? Maybe teach you a little bit of max knowledge. Corollary is something that you can quickly deduce from theorem. Okay, theorem is something that need more works. Corollary is just the application of theorem. So can you see how we apply theorem or not? So theorem need a zero beside the derivative, right? Can you make similar equation from the statement of corollary? Something equal to zero. Understand what I say, Felicia? Not really, cannot follow. Okay. Yeah, it's fine, it's fine. Yeah. Okay. So yeah, maybe one thing that you want to learn in the university is the listening. Okay, you need to listen to what people say, even if you don't understand. Even if you don't understand, you need to capture every word what that person saying. Okay, because let me tell you something. Because usually how we listen to people, do you know? Do you ever think about how you listen to people word? Most of the time, right, you listen the first phrase and then you guess the rest. 知道我在讲什么？哦，你只听了前面一句话，后面半句话是你猜出来的。Okay, so actually you are putting your thinking into people's mouth. It's not what that person wants to compare to. You understand? This is very important, huh? Okay, because even I come out with the word, the colleague is also like they try to put their thinking into your mouth. And then this will create a lot of confusion or misunderstanding. And so it's very important listening skill. Okay, that's why you come to lecture. Why not you just go back and watch YouTube, do your servlets? Okay, so okay, man. But the problem is, did you improve in your listening skill? You might learn how to calculate, but can you listen to what people say? It's a very important skill. Okay, without understanding, you should capture whatever people say. And then after you capture what people say, start understanding. It's not like understanding and then listen. No. You should listen first. Okay. Okay. So let's come back here. So how do we apply theorem here? Yeah. So if we have f prime x equals to g prime x, well, this is just saying that f prime x minus g prime x is 0. Okay. Then you can use theorem already. Okay, you have the difference of this derivative of a different function is 0. Then from theorem above, we say that f minus gx is a constant function. Okay, so that's why fx minus gx is just deferred by a constant. Okay, does it make sense? So the key here I want you to remember is if two functions have the same way that the tangent line deviate, then they are really the same graph. Not exactly the same graph, but up to a constant. Okay, so the picture in your mind could be something like you have y square, y equals to x square. Maybe you could also have y equals to x squared plus 1. Okay, not exactly the same graph, but their tangent is still the same. Okay. Okay, let's see how we apply this. Yeah. So prove that sine inverse x plus cos inverse x is equals to pi over 2 for all the x's in between -1 and 1. So x live from -1 to 1. So you might think that, oh, this is like a trigonometric identity, right? You can use the trigonometric formula to prove it. Maybe you could, okay, but we won't do it here. Instead, we will use the derivative way to do it. So how do we use the previous theorem? So you need to make a connection here. So the previous theorem has what? Derivative has what? Has constant. Okay. Do you see any constant here or not? Which one is a constant? Huh? Pi over 2. Okay, so pi over 2 is a constant. So, so right. So you realize that sine inverse x and cos inverse x is what? Is a function, right? Okay. So let's compute the derivative of this function first. Not that. What's the derivative of this sine plus x plus cos inverse x? Yeah. Can you try and go back and find what's your formula? Huh? 1 over square root 1 minus x squared. Okay, so this one is for sine inverse, is it? Okay, how about cos inverse? What's the derivative? Huh? Okay. What's the derivative of cos inverse? Check your table. Check your table. What is it? It's Jeffrey here, Jeffrey. Where's Jeffrey? Okay, Jeffrey. What's the derivative of cos inverse x? Check your table. Yeah. I don't think you can compute on the spot. Yeah, please check your table. I mean, you can check Google also. What's the derivative of cos inverse x? What is it? -1 over root 1 minus x squared. Okay, so you can see that actually these cancel out. Okay, this cancel out. This cancel out means what? Okay, from the theorem, if you have a derivative that's always 0, we know that there exists a constant c such that sine inverse x plus cos inverse x equals to c. Okay, so how to find the c? Any method to find c? Is there any way to find the c here? So this is when you should use your condition of x here. Okay, sorry. Uh, S equals to, you can find C. So we want x equals to pi over 2. Is pi over 2 living inside -1 and 1? Sorry? Pi over 4. Pi over 4 is what? Pi over 4 is equals to what? Radian. In radian. Because pi is 3 point something, right? And then you divide by 4, it should be 0 point something. Okay, then it's good. You want to use pi over 4. Okay, so let's see. Yeah. So consider take x equals to pi over 4. Okay. And then what is sine inverse of pi over 4 plus cos inverse of pi over 4? Pi over 4 is what degree? 45 degree. Okay, so what is the sine inverse of 45 degree? Is it easy to compute this thing? Calculator, where's your calculator? Hmm? This is sine inverse, this is not sine, oh. This is sine inverse, eh? Huh? This is sine inverse or not sine? Sorry? You want to use x equals to 0 instead? Okay, maybe you can do this computation, but I think it's quite hard. Okay, let's take a easier one. Take x equals 0. So let's take this is the first choice. Let's do a second choice. X equals 0. And C is sine inverse of 0 plus cos inverse of 0. Okay, so sine inverse of 0 should be 0. Yeah. And then cos inverse of 0 is 1. How about 2? Oh, yeah, right. Okay. Because this is the place where it goes to 0. Okay. Then we are done. Okay. Because we know that this function is constant, so you just evaluate at any point. It's fine. Okay, because we know that this function is already constant. Okay, just evaluate at one point. You can fix this C. But although this pi over 4 is hard to compute, right? By theory, you should get pi over 2 as well. I don't think this pi over 2 is symmetrically distributed between these two numbers. But they should add up to very close to pi over 2. I think it's exactly pi. Okay. Yeah. So one thing I want you to remember, don't be confused, is maybe sine inverse x is not equal to 1 over sine x. Okay, so please remember this. Because you might think that this is just polynomial. Because these two derivative is really different. It's very different. Okay, then 4.15 we will left as a exercise. You can try and do. Please do. Please go back and do. For those that I left for exercise, right? Actually, it's the same method that I teach in class. But we cannot do everything in detail. So I want you to try it. I try to explain new stuff in detail in class. So this time we'll eat the time that we do other exercise. Because the way that maybe other lecturer will do was, I just keep doing. I don't care what is it you do. Then do until you somehow your muscle can do it. Not your brain can do it, but your muscle can do it. Muscle memory. Yeah, but I'm not trying to do that in my class. Yeah, I want your brain can do it. Maybe you should be able to understand. But to do that, it requires time. It requires practice. You know piano. You know piano? Piano? You know one good pianist, what the pianist will do? They will like practice 8 hours every day. It's like you study 8 hours every day. Yeah, need time. It's not like you listen to me, you understand. You do in class, but you need to do exercise. Then you want to excel. Okay. Any other question before we take a break? Any question? Okay, no question. Let's take a break until 10:05. Yes. Yeah, one of them is that. There are others, right? Yeah. And also the tutorial, the question exercises like this after each chapter or section, there's an exercise. Yeah. I mean, you don't need to do all, but at least you need to do until a stage that you you think that you know. Yes.
I want to prove that uh, plus is to y1 at units x. Oh, it's equal to y1. So it's let's see.不就相当于是本身还是有点公式了，因为你 sin x 加 sin 加那个 cos x 存在的一，本质上不也是有点公式吗？接受，我的上面的函数的二分之四分之派加四分之派等二分之派，几何分。
This one is fine. How do you get from this to this?
It only has one solution.
It has one solution.
Yeah.
Why?
So because the range of y and y2 is this.
Okay. And then there's only one solution.
One is in the
Yes. Is here, and another one is yes.
Okay,
The
okay,
one
sure,
was-
sure, 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 sure. I mean, like, okay, sure, sure, sure. Yeah, yeah. I think those you need to prove then. If you can prove those things, then that's fine.
I can compute
Mm-hmm.
I can compute cosine. As you can see, that's y plus x,
Mhm.
and that's a 2 point that the the 2 point of this one, this,
Hmm.
and just they are symmetry.
Okay. Then
Then we want to find um, find this plus this. That's right.
okay. Then
And then they are same with
mhm.
this plus this.
Okay.
And so it's for so it's
Why is it powerful for those points?
because um the how can I say means reflection of the light. 不是那个意思，就是this point and this point symmetry, and so if you want to find his reflection on the y, and just equals to this reflection on this one. Same.
Wait, you try to write it out. You try and write a version and then send.
Okay.
Yeah, try write everything.要印东西的，这个 OK。可以去到第4楼，对，然后你电梯走上，然后你转左，然后转左有一个复印机的地方，然后应该我忘了我在哪一家，应该是第3家吧。你看一下哪一家有在印，或者它卡住了，你可能要加纸进去，纸在那传没问题，你们说。Hello. Okay. Let's continue first. I will take attendance later. Hopefully, I will release the quiz if earliest by weekend. If not, then next week. By next month, Wednesday or Friday, we should be able to discuss the solution. Yep. Yep. Quiz 2. Second quiz will be happening on week 7. Sorry. Also, it's the same method. Yeah. 24 hours. It will be Monday. Last time was on Tuesday because Monday is a public holiday. It will be on Monday, 3 to 3 again. 3 p.m. to 3 p.m. Okay. Yeah, so chapter 3 and 4. So hopefully we can finish chapter 4 by next week. Okay, so let's continue. So we are actually almost at the L'Hopital. Maybe if we can't do it today, we will do it next week. So to motivate that, we will start with monotonicity theorem. Okay. So if your x is always having a positive derivative, okay, this means your f is increasing. If your x have a negative derivative, then this means your f is decreasing. Okay, so does this make sense? Does this make sense? Yeah. Yeah. Who say yeah? How do you make sense of this? Again, tangent line. Okay, again, tangent line. So what does it mean by positive derivative? How your tangent line looks like? Okay, so really there are two basic lines you should remember, right? Y equals to x and y equals to minus x. Okay, so if it is positive, then it is drawing from the second quadrant to the third quadrant to the first quadrant. Okay, so a positive gradient of tangent line maybe looks like this. Okay, how about negative? If it's negative, what happens? So you are on the second quadrant drawing down to the fourth quadrant, something like that. Right. Okay, no matter how you draw, it is like going down. Okay, can everyone see it? So maybe let's start with. Okay, does it make sense? So we can try and connect all these tangent line. Make sense? Okay. But another way to remember, right? Greater than zero is like positive, right? So increasing. Less than zero. Okay, can you remember so far? And later we're gonna use it to find maximum minimum later. I think for this interval, for finding interval for f to be increasing, decreasing, can we skip? Can we skip or you want to do? Do you know what to do? If I ask you this, find the derivative first and then determine which x you get positive greater than zero, what's x less than zero. Okay, should be fine. Okay, let's skip this two. Let's start with a very interesting one, which is a first derivative test. Okay, so these are the way to find local maximum and local minimum. Previously, when we want to find local maximum minimum, we just do by definition. Okay, use the neighborhood if you still remember. Okay, the neighborhood. But now we're going to use derivative to find it. Okay. So if you look at the picture below, so in the first picture, okay, to become a maximum, what do you need to do first? You need to fight very hard to go up. And then you will go down. So on one side, you are increasing. On the other side, you are decreasing. Okay, so meaning on the left-hand side, you have positive gradient. On the right-hand side, you have negative gradient. So you go up, go down. So this is the hill. Okay, so this is the maximum, local maximum. And to be a minimum, how do you become a minimum? You go down first, then you come up. Okay, you go down first, you come up. So you found that calculus very hard, or you're feeling very down. And after you do some exercise, you feel better. Yes. Okay. So this is how we find local maximum and minimum. So if on the left hand side it is positive, meaning increasing, on the right it's decreasing, then you are local maximum. But on the left, you are decreasing first, and then on the right you increase again, then you are a local minimum. But what happens if you have both sides the same sign? Meaning what? They are just on the step of increasing or decreasing. So there's no local extreme point here. Okay, so let's do 4.18. Let's do this one. So to find the local extreme value theorem on minus infinity to infinity using the first derivatives test. All right. Is the aircon working? Feel very good. Okay. So meaning that we want to find where it increasing or where it decreasing. Okay. So let's do it. I mean for the derivative. So note that f prime x is equals to 3x squared minus 6x minus 9, like that. Let's make it a little bit simpler, factorizing this polynomial here. Okay, so this is actually a quadratic polynomial, right? Okay, with root -1 and 3. Okay, so there are a few things you want to determine. So when is this function greater than 0? Any idea? Greater than 0. When is this function greater than 0? Actually, this line is y equals 0 line, right? Okay, so for all these top part here. So these are all the point that is less than -1 or greater than 3. How about all the f prime x that's less than 0? And these are all the point here. Okay, so these are the point from -1 all the way to 3. Okay, is it okay? Okay. Okay, so maybe we can record this sign here. So let's say -1, 3. Okay. So on -1, there's a negative sign for your derivative. And -1, sorry, here is positive sign, greater than 0. -1 to 3 is a negative sign. And then 3 beyond is positive again. So meaning what? How's your function looks like? You're increasing and then decreasing and then increasing again, something like that. Okay. So what's your local extreme value here? First, where's your local maximum? Where's your local? Aaron, where is your local maximum? Where your local? Right, x equals to -1, you have your local maximum, minimum, -3. Okay, so f of -1, which is equals to let's say 3 times -1 minus 3. -1 plus 1 actually is 0, right? Is it 0? Hey, sorry, I subbed the wrong function. The actual function is -1 cubed minus 3 times -1 squared -9 times -1 plus 12. I guess is 17. Okay, so this value is actually a local maximum value of f. And f of 3 is 3 cubed minus 3 times 3 to the square minus 9 times 3 plus 12. This is actually minus 15. And this is a local minimum. Okay, value of. And these two together are the local extreme values. Okay, if you don't believe, you can plot it out, right? You can plot it out. Use GeoGebra. Anyone using iPad here? iPad? You guys using iPad? iPad? You know iPad can graph? No, you guys don't know? Maybe I can try and demonstrate. This is the new function that come out from the iOS last year, I think. Last year we already got it. So just now is let's write it. X equals to x cubed minus 3x squared minus 3. So let's try. I seldom use this. Oh, maybe okay, maybe the iPad need Y instead of FX. Let's try. Yeah. So iPad doesn't recognize FX. Okay, insert graph. Okay, so this is the graph. So let's make it larger. So can you see our local max and local means here? At minus x equals to -1 as s equals to 3. Yeah. Okay, so here. Actually, this iPad can do more things. Let's say your C can vary, right? Actually, you can change this C, you see? And then the graph can change. You see? Can you see the graph changing? Okay, you can change the constant actually. Okay, yeah. Can we change the 9? Yeah, we can change the 9 as well. Can you see this variable here? Okay. Hey, the screen is not changing, but I'm changing here. How come? Is it like, yeah, okay. Or maybe a bit too fast. Ah, okay, never mind. See? Yeah. Okay, so you can change this number here as well. Quite lag or using iPad notes. Yeah, this number can be changed. Yes, very useful tools here. Okay, yeah, again, how about I let you try which one is better to try? I think let's try 4.20, 4.19. I let you do homework. I let you try for 3 minutes and then we can check answer together. 4.20. Okay, you do it. I try take some attendance. C 和乐天、陈乐天、瑞阳、若石、施曼、一南、玉涛、玉涛、陈玉涛、陈义哲、戴立伟、邓瑞阳、潘泽汉、吴佳来、何嘉诚、吴佳怡、黄启军、黄义清、季俊义、 孔相思，雷依林，雷依林，雷依林，李冰珍，吕家腾，林浩云，林文基，刘汉祥，OK，刘俊杰，刘俊杰，哦，yeah right，刘新阳，卢万达，卢新月，罗玉恒，马一田，苗冰城，倪浩然，Desmond Desmond Desmond toilet OK Tommy yep 琼毅 yep 英杰张英杰 OK Opagami Arthur Arianto Jose Hisham Daniel Hashim here or not Hashim bin Yusuf Hashim oh disappear for a long time Madia yep Aaron Alicia God Gunakanti okay Margaret okay Hassan Khalid Hassan Khalid here for a few days Javed Gabriel okay yeah Jeffrey God yeah Purity God Chen Fan He Yahu yeah Hu Ye God Guo Hongliang may I know how many of you are coming here using replacement test? Meaning maybe you don't pass the requirement, but the university decide to give you a test. Then you can come in. Any one of you? No? No? Because I know some of you was doing replacement test. I think this thing actually is quite common in this university because if you know that this university actually is a private university, so they need to attract as many students as possible. So they want to recruit you as long as you meet certain requirement. But sometimes that requirement could be low. Okay, so you might need to be very hardworking. Okay, if you meet a low requirement to come in. Does it make sense? Does it make sense? Okay, so I see a lot of cases already actually. Student dropping out. Okay, because they cannot keep up with the work here. So if you really cannot keep up, you have to I mean there's few ways to keep up. You can come to my office hour or you can try and find some friends, study together, and do revision together. Okay, so I'll make sure you get help. Okay. Otherwise, you will just drop from the university. I think it's really tough to study alone, unless you are very good. Okay, if not, try to get some friends to study together. Okay, yeah. All right, let's do together. Let's check. So similarly, to use the first derivative, we need to get our hands on the first derivative, which is 1 plus 2 cos x in this case. And we want to see where it's increasing or decreasing. So to inequality, you want to tackle f prime x greater than 0 and f prime x less than 0. So f prime x greater than 0. When is it greater than 0? So meaning that your cos x has to be greater than negative half. Okay, so when does it happen? So maybe it's better you want to draw your function out, cos x. Okay, so the x's you compare here is just from 0 to 2 pi, so this is all good. Okay, so where is negative half? Maybe at the bottom here. Okay, so you want to find what's this 2 point. Okay, so this 2 point is, what is it? Sorry, 2 pi over 3. Okay, so one of it is 2 pi over 3. And then the other one is 4 pi over 3. 3. Yeah, okay. So from here we can see that if you want to stay above, okay, you want to stay above, meaning this part here, then your x's need to stay at 0 up to 2 pi over 3. And then on the other side is 4 pi over 3 up to 2 pi. Okay. So similarly, if you want to stay below, okay, so if you want to stay below minus half, then your x's need to stay in between 2 pi over 3 and 4 pi over 3. Okay. So maybe it's a good practice that you try and list out all these positive and negative sign here. So it is break into 3 region, 0 to 2 pi over 3, 2 pi over 3 to 4 pi over 3, and then 4 pi over 3 up to 2 pi. So you start with positive, and then negative, and then positive. So you go up, and then come down, and then go up again. Okay, similar pattern that we had from the first example. Okay, so you have a local maximum at x equals to 2 pi over 3 and local minimum at x equals to 4 pi over 3. Okay, so try and do the computation, write out that f of 2 pi over 3 equal, what is that? Is the local max of f, and f of 4 pi over 3, and then what is that? It's a local minimum of f. Okay. Question? Any question? Kind of straightforward. Yeah, increasing, decreasing, decreasing, increasing. Okay. Okay. So Felicia, if you got a point, the function increase on one side, increase in the other side, is it a local maximum or local minimum? One increase, on the left side increase, on the right side also increase. Is it a local maximum or minimum? It's minimum. Hmm. Hmm. Yeah, increase and increase. Yes, you don't understand. That's right. That's what I said. Increase. No, it's not a local extreme point. Right. So if you increase on one side, you increase again, then this is not any local extreme. Okay. Also similarly, if you have decrease, is also not a local extreme. This is not what I say, right? This is what you thought, right? It's not what I thought. Okay. So make sure you know what I think, not you think. Okay. Yeah. Okay. So try listen, listen to what people say. This is a very important homework. Okay. You think is what you think. I think is what I think. Okay, so try and understand what people think. Okay, next, we'll use another method to find extreme value theorem here. So before that, we'll define what's concave upward and concave downward. We say that f is concave upward if the graph lies above all its tangent line. Okay, that is on the left side here. Okay, so this is concave upward. So you can remember that your graph will stay above your tangent line. Okay, how about concave downward? Meaning your graph will stay below its tangent line. Can you see that the graph stay below tangent line? Okay. So there's another two possibility, right? You could have something like this. Decreasing. Okay, still concave upward. Okay, on the other side is decreasing as well. Okay, if you learn physics, right, there's a concave lens and a convex lens, right? Upward and downward. Does this match the terminology you learn in China or not for Chinese students? Yes, what's concave outward in Chinese? Some. Also some. Because I remember someone told me that the convention is different. I don't know it's true or not. Okay. If it is okay, then that's fine. Okay. So so when do we know that a function is concave upward or downward? So let f be a differentiable on the open interval. We say that f is concave up if f prime is increasing. Okay, we say that it is concave down if f prime is decreasing. Okay. Does it make sense? Let's check. On the left picture, right, is the derivative increasing or not? Is it increasing? Getting steeper. Okay. This one, the second case, is this increasing? No. 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 You get less steep, but your gradient is getting more positive. Right? Does it make sense? Let's say, I mean, on this side, right? Here is y equals to x minus x, sorry. Y equals to, let's say, minus 100x. But here, y equals to negative, let's say, 0.5x. Okay, so you're getting more positive. Right? Yeah. Getting more positive. So you go from negative value to positive value, increasing it. Although less steep, but actually it's because you're getting more positive already. You're getting more to the other side. So similarly on concave, okay, so you can see that if you are increasing, right, then this tangent line is getting less steeper, okay, close to the horizontal line. And then on the other side, you are getting more negative. Okay, so decreasing. Okay, please convince yourself about this. So another way to check is second derivative. Okay, second derivative. So if your second derivative is greater than 0, then your function is concave upward. If your second derivative is negative, then your f is concave downward. Okay, precisely because of this increasing and decreasing. Okay, because if it's increasing, then your velocity of your velocity, velocity of the velocity is positive. What's velocity of a velocity? Margaret? What's the velocity of a velocity? What's the velocity of a velocity? Acceleration. Okay. And Yeah. Okay. So if it's decreasing, if your first derivative is decreasing, then your second derivative is a negative. All right. So let's do this question together. So you want to determine whether this is concave upward or downward. We will just use the concavity theorem that we know just now to check when is f double prime is greater than 0 and less than 0. Okay, similar technique just now. Right. Just now, the positive and the negative of first derivative will tell you what's local maximum or minimum. But now the positive or negative of second derivative will tell you whether this function is concave upward or downward. Okay, let's try and do this. So note that what is f prime x here? So let's quickly compute 3x squared minus 6x minus 9. Similar function, huh? I think we differentiate this before. Now we need to differentiate the second time 6x minus 6, okay, which is 6 times x minus 1. So let's see, okay, when is it this function here greater than 0 and less than 0? So, well, who control the positivity or negativity here? 6 cannot control, right? 6 is already positive and changed. But the problem here is x minus 1. Okay, so when is x minus 1 greater than 0? As long as x greater than 1. Okay. Maybe you can draw this as well. Either you want to use algebra way to think about it or you draw it. So if you want to draw it, the graph like that. So positive side is anything beyond x equals to 1. Okay, so when x greater than 1, it is positive second derivative and negative for x less than 1. Okay, so if you draw the real line here, anything after 1 is positive, before 1 is negative. Okay, so f is concave upward on interval from 1 to infinity, and f is concave downward on negative infinity to also. Okay. Okay, should we try and draw this curve? I think we did draw right just now. So let's make this curve to what is it? -9. Let's make it -9. Oh, now it's better. It's continuously changing now. It just now was stuck. -9 like that, and then okay. This one is 12 plus 12. Okay, just now we say that when is it concave upward? Felicia, when is it concave upward? Okay, 1 to infinity. So can we see that here? So let's draw it. Maybe zoom it a bit. Can we zoom? Cannot zoom. Make it larger. Okay, like that. Can I draw something on here? Oh, I can. Okay. So concave upward meaning the tangent line will stay below the curve. Okay, so like this. And then the other side, the tangent line will stay above the curve. Not straight. Maybe a bit thinner. Okay. Okay. Make sense? Maybe that makes it a bit thinner. Okay, what happened? Okay, why can't I draw line? Okay. All right. Then in that case, I'll skip this question. 4.22 is the same way. Let's continue. All right. So we'll call a point CFC an inflection point of the graph F if it is concave one up on one side and concave down on the other side. Okay. So this is another generalization of what we have from first derivative, right? First derivative positive on one side, negative on one side, you will learn that it is a local extreme point. But let's say your second derivative is positive on one side, negative on the other side, then this point is what we call a inflection point. An inflection point. This is not a local extreme point. An inflection point. It's like you are doing a turn around at that point. Okay, it's almost like a reflection point for your graph. So if your point is an inflection point, then either the second derivative of this point is zero or it doesn't exist. Okay? So to talk about inflection point, we are not talking about first derivative now. We are talking about the second derivative, which is the stationary point for your derivative. So it's the stationary point for your derivative. So we go up another level. Okay, so inflection point is another layer of derivative we need to do. Okay, so let's find the inflection point for this function here. Okay. So let's do it. So we want to see where it concave and concave outward and downward. And then if we know that before this point is outward, and then after this point is downward, or the other way around, then this is an inflection point. So we need to compute up to second derivative. So let's do it. So let's differentiate this. What do you get? 1 over 3 times square root 3 of x squared. Okay, I mean, you can write it to a more compact form to do integration later. Sorry, differentiation later. So if you differentiate this, you get negative 2 over 9 x to the minus 5. Okay, so let's see when is this positive and negative. The second derivative. Okay, so can you quickly see when is it positive or negative? Who can control the sign? Only x. Okay, x can control the sign, but here is quite straightforward. There's no very hard factor here. You just plug your number in, you'll get your sign already pretty much. Okay, because if you plug a number in, what do you need to do? Take power to 5. Okay, take power to 5 means what? This is an odd power. If you are negative, you will stay negative. If you are positive, you will still stay positive. Okay, but then you need to take cube root. Meaning what? If you are negative, you still stay negative. If you are positive, you still positive. Okay. But then there's an extra negative sign there you need to take note of. So if you put a negative value into x, you take the power, you still negative, but negative times negative, you get a positive. Okay. So when x is less than 0, okay, what am I doing here? When x is less than 0, then your f prime x should be positive. And if x is greater than 0, then your f prime x is negative. So meaning f is concave, downward on 0 to infinity, and f is concave upward on negative infinity to 0. Okay, so this means what? You have one side of 0 is concave downward, the other side is concave upward, meaning 0 of f0, which is 0 to, is an inflection point. Okay, so something to note here is, if you really compute f prime prime 0, right, actually it does not exist. Okay, if you see from the formula there, you need to divide by 0 also. So you can compute that the limit doesn't limit on the secant. So it's an inflection point, and then the second derivative is not defined there actually. Okay. Well, you can do similar thing, right? You can try and draw this to make sure what you compute is okay. Y equals to x to the 1 over 3 plus 2. Can recognize or not? Oh, can recognize. Insert graph. Okay, so where is our inflation point 0? So this is not big enough to see. Okay, like this. Is it not defined on the other side? It should be defined, right? Hey, why there's no the other side one? Okay, where's the other side? How come? Let's see. Yeah, this is quite big, right? This x. Let's try GeoGebra. X to the 1 over 3 plus 2. Wow, GeoGebra is better. Okay, so can you see the inflection point here? Yeah, if you draw tangent line on one side, it will stay above. Tangent line on the other side will stay upward. Is it right? Concave outward is anything greater than 0. Oh, concave downward is 0 to infinity because the tangent line will stay above. And then, okay, maybe let's import this image. Okay, so you can see that if you're going to draw the tangent line, it's like this, right? And on the other side. Okay, so here is a concave upward because your graph stay above your tangent line. The other side concave. downward. Okay. Question? Got question? No? Okay. All right. I think this is for the inflection point. Okay, let's go to the next bit. Maybe we'll do one question and then we'll take a break. So next bit is a second derivative test. Okay. So first derivative test help you to find local maximum or minimum. Second derivative test also help you to find local extreme value theorem. Okay. So once you find your stationary point, okay, this one only works for stationary point. If your local maximum or minimum is not found by this, then this might not be helpful. And so this is only helpful for stationary point. Quite restrictive actually. Okay, but please remember, don't just compute second derivative without thinking. So once you know your stationary point, and you can find your second derivative. If it is negative, then then FC is a local maximum value. But if F prime C is positive, then FC is a local minimum value. So something to note here is if F prime or F prime prime does not exist, then this test is pretty much useless because you cannot check positive negative. Or even if it both happens, but you become a stationary point of your F prime, then it's not useful as well because just now you see that it could be an inflection point. Then it could be an Is it counterintuitive? Negative become a local maximum, positive become. Any way to think about this? So we know that when it is less than 0, it is concave downward, right? Okay, concave downward. Actually, this is what you know just now, actually. Concave downwards means what? Your graph stay below. Okay, your graph stay below. Is it true that your graph stay below when you have a maximum? Below tangent line. Okay. F prime prime x greater than 0 means what? It concave upward. So meaning your graph stay above tangent line. Correct or not? When you have local minimum, is your graph stay above your tangent line? Okay. So this is the idea. Okay, you can remember here. Okay, makes sense. Okay, quite strong. Also easy check. Okay, easy check for stationary point. If the derivative is easy. Any question? Question? Can remember the test? Because I think a very common mistake that people will make in this test is when m prime prime c greater than 0, it is a local maximum. They swap it because they think positive are very big. Maximum are big. But the idea of big is here. This is the idea of big. Okay, when this is positive, the graph stay below. Okay, the graph stay below only because you stay below. Okay, if you stay above your tangent line, meaning you have to come down for somehow. Okay, your tangent line stay below. Okay, please remember the swap here. Please don't make this mistake. Because you don't know what happened, you just memorize. So that's why you got mistake. But the point is this two pictures. Okay, where your tangent line stay. Stay below or stay above? Is stay below, is it concave upward or downward? Think about it. Okay, how about let's break here and then we'll do exercise later. Let's break until 11:05. attendance list. Again for you. Oh, well, I think I book it. Okay.
Okay.
Hello. Okay. Let's continue with the examples. So we're going to find local maximum and minimum of this function. Okay, they define from negative infinity to infinity. So are you good with this domain here? Because it's just a polynomial function. Okay, it's very good. Good for differentiation. It's good for continuity as well. So we're going to use second derivative test to find local maximum and minimum. All right, so to use second derivative test, obviously you need to compute up to second derivative. So the first one you will get 4x cubed minus 6x squared. So if you factorize it, you get 2x squared times 2x minus 3, okay, for later use. And differentiate it again. Maybe you want to use the first presentation to differentiate, is easier, differentiating term by term. Or you want to use the product rule on the second presentation, also fine. Okay, which is 12 times this one. So to use second derivative test, you really have to start with a stationary point. Okay, you need to start with a stationary point. So you need to check when is f prime x equals 0. Okay, so meaning 2x squared times 2x minus 3 equals to 0. Okay, so there are 2 points of it. So either x equals 0 or x equals to 3 over 2. Okay, 2 points. 2 stationary points. And what do you do next? So for second derivative test, you just need to evaluate. Okay, just evaluate at these points. So what is f prime prime 0? It's just 0. And f prime 3 over 2 is equals to 9. Okay, we'll quickly compute it. It's greater than 0. Okay. So by second derivative test, what can you say about f prime prime 0? Is it a local maximum or minimum when second derivative equals 0? Is it a local maximum or minimum? Alicia, your second derivative is 0. Is it a local maximum or minimum? What? Huh? Nothing. I don't know. Okay. Most probably is inflection point. Okay, so maybe you can compute what is before 0, what is after 0. But if your second derivative is positive, that means you are local maximum or minimum? Minimum. Okay, local minimum. Okay, so by second derivative test, okay, your f of 3 over 2, if you go and compute it, it is negative 27 over 16 is a local minimum value. Okay, but the test is not conclusive for f0. Okay, it's not conclusive for f0. Inconclusive. Okay, it's not conclusive. But can you see when x is less than 0, what's your f prime prime x? What's your second derivative? Huh? Your f prime x is 12x times x minus 1, right? Is less than 0 times what? Negative 1, is it? Yeah. So it's something less than 0. But if you are greater than 0, what do you get? Then your f prime second derivative is greater than 0 times -1. Is it? 0 is greater than 0 times negative. Okay, which is greater than 0. Okay, so actually, 0 f0 is an inflection point. So actually, I plot this out for you to confirm what we computed. Yeah, so this is the graph. Okay, you found a local minimum at 3/2. And 3/2 is 1.5. Okay, so 1.5. And then at 0, you have a concave downward, upward on one side, concave downward the other. Okay. Any question? Question so far? No? Okay, I'll let you try another problem. How about I let you try for 3 minutes, see how far you can get for 4.25, and then we can discuss. Okay, try this. I think this derivative is a little bit challenging. A little bit. So in the previous case, there's no local maximum. Okay, so there's local minimum. By the way, you can discuss, you can talk with your friend, it's fine. Just that you don't talk when I lecture, is fine. If I don't lecture, you can talk. You can discuss with your friend. Okay, let's see. Have here. Okay, let's check the derivative. Anyone can tell me what's the first derivative here? What's the first derivative? -1 over. Okay, someone say something. -1 plus 2. -1 plus 2 plus p. over p square dot multiply 1 minus p to the square. Everyone got this? Same? No? What do you get? Yeah, what you get? You tell me what you get. Tell me what you get first. You same? Same, ah? Sorry? 2p? What? What did you get? Minus 1 plus 2p. So is it 2p or p? 2p, ah? Okay, so let's write down what I get. I get minus 1 over p squared plus 1 over 1 minus p squared. This is what I get. So if you want to make them the same, then same denominator, meaning, then I think you will get this, right? And then you expand it out. 1 plus, sorry, minus 2p plus p squared plus p squared. So in the end, you got p squared cancel. You get 2p minus 1. Okay, so you get a 2p. Okay, good. How about next one? Second derivative. So I'll write down mine. 2 over p cubed plus 1 over 1 minus p cubed. Okay. I'll just leave it in this form because I think it's easier to calculate. Right, so we need to find what's the stationary point for G. Okay, so what's the stationary point for G? So that's amounts to saying that G prime is 0. Then to make this 0, we have to make 2p minus 1 0. To make this 0, we need to make p to be 1 over 2. Okay, so 1 over 2. Okay, then if you want to use second derivative test, that means you have to evaluate your second derivative at 1 over 2. What's this? 1, sorry, 2 over 1 over 2 cube plus 1 over 1 minus 1 over 2 cube. So I guess you get 24. 24? Okay, good. So 24 is positive, meaning this point is a local minimum. Good. So by second derivative test, G of half is 4, is a local value. G, and G has no local max. Okay, so I plot this graph as well. This graph looks like this. Okay, so can you see a local max? Local mean, sorry, local mean is at half. Okay, so here is half. This point is s equals to half. Okay, so there's no other local maximum or minimum. Make sense? Yeah. Let's see. So there are two more exercises. For 4.2 and 4.6, 4.2 is a bit polynomial-like. It's easier to do. I think I'll just leave it for you. But we will try and do 4.27 together. This is kind of fun. Okay, this question is kind of fun. Actually, it's a similar question, but we add in a component of increasing and decreasing. Okay, so if you look at the 4.27, there are three tasks here. So first task is to find increasing, decreasing interval for f, And then B, determine the local maximum and minimum. Lastly, find the interval that your function concave upward or downward. Similarly, find all the inflection point. This is all what we have doing for just now, past hour. So this three exercise here actually, the skill that require you to do was to find what's first derivative, second derivative, and then determine where it is positive, where it's negative. Right, let's do it one by one. Yeah, let's do it one by one. Cool. Let's do this one. This is very fun, this question. Okay. I have some fun preparing this question. So for the first part, what you really need to do was you just find your first derivative. Okay, so let's find the first derivative. Let fx equals to e to the 1 over x. Okay, so how to differentiate this? Go back to last week theory. Okay, you got a basic function, exponential function. You got another basic function, which is 1 over x. And then you put them together by a composite. So meaning you need to use a chain rule. So by chain rule, f prime x is what? Equals to negative e to the 1 over x over x to the square. Okay. If you're not sure how you get this right, make sure you write down what is your y, and then what's your u. Okay, and then you do the derivative and then multiply together. Okay. So by chain rule, you get this. Well, so increasing, decreasing. Okay, so you want to find when is it greater than 0, when is it less than 0. Is it possible that this value greater than 0? No, why? Why? Because x squared is always positive and is also always greater than 0. Okay, it's always greater than positive. Yeah, so positive over positive is still positive, but positive with negative, you get negative. Okay, so e exponential function is a positive function, x squared is a positive function, so you only get positive value. But you have a negative sign in front, then you will always be negative. So since this function is very interesting, later we're going to draw it out. Since f prime x cannot be greater than 0, okay, why is it not greater than 0? Because exponential function greater than 0, exponential function is, and the square function are always positive. Or I would say non-negative. 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 But you can see that this function shouldn't take x to be 0 as the domain, right? Because 1 over 0 doesn't define. So it is no way increasing. So how should you think about this function? It's always decreasing, going downward. Okay, not sure where you can go, but going downward. Okay, so also since f prime x is always negative, f is decreasing. Okay, cool. So this is a decreasing function, no way increasing. Okay, next, we're going to find local maximum and minimum. So we could try and use second derivatives. Do we use second derivative test? Okay, if you're going to use second derivative test, maybe you should differentiate this again. But let's ask a question first. Is there any stationary point? Stationary point? Huh? Any x such that fx equals to 0? I mean f prime x equals 0? Can f prime x equal 0? No. There's no stationary point, so don't waste your time differentiate second time. Okay, so note that there's no x such that f prime x equals 0. Okay, because e to the 1 over x equals 0 is actually impossible. Okay, your exponential function cannot get to 0. Okay. But then, do you have singular point to take care here? The singular point happening here. So it is singular at x equals 0 as well, right? But that point won't. That point, is it the local max or minimum or not? Should we check it? Okay, so singular point, this function has a singular point. Okay, there is a singular point. Is singular point of f, which is 0 x0. Oh, so not defined. Oh. Okay, it's not defined. So actually, there's none. There is no singular point of f at s equals 0 because f is not defined there. Okay. No local max, no minimum, no local minimum. This guy keep going down. Okay. Find the concativity. Okay. Try and find this concativity. So this concerning to find the second derivative. Okay, let's differentiate again. So now we're going to use quotient rule here. Okay, so maybe you can do it together for differentiating e to the 1 over x squared, negative of it. So if you use quotient rule, what do you get? Okay, so if you simplify your quotient, you get something like this. Okay, again, quite nice here. E to the 1 over x is positive, and then x to the 4 is positive, but your sign could change now. Okay, because of this 2x plus 1. Okay, because of this 2x plus 1. Okay. So for f prime x to be greater than 0, you want to make sure that your x is always greater than minus half. Okay, but your x obviously cannot be 0. And for f prime prime x to be less than 0, you want your x to be less than minus half. Okay, so altogether, what you will get is f is concave upward on minus half to 0, and also 0 to infinity. Okay, so here I split it out because at 0 is not defined. Okay, so I split it up. On the other hand, it is concave downward on the left hand side of minus. I think this is open as well, right? Okay. Can you imagine what this graph looks like? So where is the inflection point here? Okay, so from here, we deduce that the inflection point of f is um is minus half of f minus half. What's this point? What's our formula? Yeah, minus. Do we have minus? No, e to the 1 over x. So to the 1 over minus half, which is minus half of e to the negative 2, like that. Okay. So there is an inflection point, and then it's going decreasing. How should this graph look like? Can you imagine or not? Imagine. When x get to 0, what happened? When s gets to 0, 1 over s get very large. And then e to the very large number also very large. So it's like coming from the sky, decreasing. On the left, on the right of the 0, I mean, decreasing. How about on the left of 0? It's a very negative number, right? So 1 over a very big negative number is a very small negative number. So e to the very small negative number is very small also. Okay, so you come from a very small number and then decrease again. So I mean, I try and sketch it. It's like this. So from here, can you see inflection point? Can you see inflection point? So if you try and draw the tangent line, right, it's like always concave upward on the right of 0. But on the left of 0 is like concave downward. Okay. But just now, where is the inflection point? Negative half. Okay, so negative half is on the right left hand side of 0. Is it not showing up? Here. Can you see concativity here or not? Maybe I remove my tangent line. Can you see it? Yeah. Can you see or not? Can you see it? Not big enough. Okay, this graph is not big enough. Okay, so you should zoom it in. So I zoom it in. So can you see concativity here? Okay, it's a very slight change, very small change. Okay, does it make sense? Okay, so sometimes you need to really zoom in to see. Okay, you cannot just see from the far of the graph. Okay, can you see that there's like a slight changes like that, very slight, very small change. Okay, until you cannot differentiate if you didn't do the calculation. Okay, there's a very slight changing here. Okay, here, this is the changing. Okay, cool. Question? Any question? Currently? Okay, you okay? Okay. Feel free to ask if you have any question. Yeah. Okay, so try and work out 4.26 yourself. It's exactly the same method. Okay, so maybe how about I draw this 4.26 right there. Can you see where's the local max, local mean? On this graph, can you see which one is local max, which one is local mean? And where's the inflection point? Huh? Where's the local mean? Where's the local max? Any local max or local mean? You need a larger Okay, since the left and right is the same pattern, right? So let's zoom in until this special part here. Where's the local max? Where's the local min? 4. 4, around 4, yeah. Local max is around here. Local min is 0. Okay, because if you make neighborhood around it, everything else is greater than f0. And you make a neighborhood around f4, everything else is below it. So can you see concavity happening here? Any inflection point? Any inflection point? Or to think about concavity, right, you need to think about this tangent line here. Right. Can you see inflection line, inflection point? Where's the inflection point? 6. This one, this is 6. Yeah, that's 6, F6 here. Okay, because before it is concave downward, and then after it is concave upward. Okay. Like a S shape. Okay, when you have an inflection point, it's like a S shape. Okay, have a S shape. Okay, so the S we have just now is pretty small. This is a small S. Okay, I think we still have a little bit more time. Maybe we can go to your favorite, L'Hopital. Finally, in lecture 10, we met this L'Hopital. Okay, so why do we introduce it now? Because you need derivative. Okay, so when can you use L'Hopital rule? So ever since after this lecture, you can start using it already. Please don't misuse it. Please don't misuse it. Luckily, you don't do L'Hopital rule in the first quiz because in the other class, they use L'Hopital rule. We don't give much. Okay, yeah. Luckily, you don't use it in the first quiz. Okay, so when do you use L'Hopital rule? So basically, when you want to compute a limit of the ratio of two functions, but you realize that if I just do substitution on the numerator or denominator, we get something, some intermediate forms here. Okay, for example, 0 over 0, infinity over infinity, or even plus infinity over negative infinity or negative infinity over positive infinity. All these are characterized as infinity over infinity. Okay, we don't care about the sign. Then you can resort to a simpler calculation, which is you just take the derivative on your numerator and the derivative on your denominator. And then you compute the limit of this ratio. Okay, then you can do it successively if you still met these intermediate form until you can evaluate the limit. Either it is exists or not exists. Okay, until you can make a decision whether it exists or not. Okay, make sense? Okay, prove it. To prove this, you need to change your degree. Please enroll in MAT degree. I will teach you how to prove it. Because to prove this, this is like involving. It's pretty involving. It's very involving. Yeah, to prove this, actually, even the MAT class here, they have to wait until the analysis course, which is in their second year, analysis 1. Okay, we need to use epsilon delta to prove this. This is very involved, very interesting proof, but very tedious. There's a lot of cases to check, and there's a conversion to take care here. A lot of convergence. Okay. So we won't attempt to prove it here, but we will learn how to use it in this class. Okay, so let's try. Okay, so we want to use L'Hopital rule to evaluate these two limit here. So why do we use L'Hopital rule? So if you look at the first one, what happened here was so by L'Hopital rule, okay, so what you observe here was you will get an intermediate form of 0 over 0. Okay. So this is when you can use L'Hopital rule by just differentiating the numerator and also the denominator, where these two limits are the same. Then you can compute this limit, right? 1 over 2x. Okay, it's continuous at s equals 2, so you get 1 over 4. Okay. So, okay. Okay. How about the second one? Maybe let's compute the second one. Sorry? 1? 1. Why is it 1? So you have an intermediate form of 0 over 0 as well. So you can differentiate top and bottom. So you get cos x over 1, which is 1. Very good. Okay. Yeah. Sin x over x, I think last time we also, also introduced this limit for you, right? The special limit. Okay, it is 1 because when x gets to 0, sin x really looks like a linear map. Yeah. Oh, regarding your friends talk about proving L'Hopital rule, right? So you see there's a f prime involved here. So how we introduce f prime is actually we need to use mean value theorem. So this proof is we need to use the mean value theorem stuff inside here, maybe a few times. Okay. Yeah. So this is it. How about the next one? I think it's very similar. So let's go to next non-trivial one. We still have 8 minutes, right? Quite good. So let's see. Let's find the next non-trivial one. 4.29 is similar. 4.30 is similar. 3.1 similar. 4.32 maybe try 4.32 here. Okay. Let's try this. So sine, wow, a bit lag, very lag. Very laggy. Okay. So we want to use L'Hopital here. Is it possible? So if you put 0 into your numerator, x equals 0 into the numerator, then you get 0 minus 0. Okay, is 0. 0 to the cube also 0. So the intermediate form is 0 over 0. Okay, so you can use the L'Hopital rule here. Sorry? Minus 1 over 3. 6. Okay. You just do once and then you can get it. I don't think so, right? You should do a multiple time. Yeah. Okay, good. So let's try it. So if you do it the first time, you will get cos x minus 1 over 3x squared. Okay, but if you try substitute 0 into x again, you get 1 minus 1, 0 on numerator. 3, 0 squared, 0. Okay, so you get an intermediate form of 0 over 0. So apply L'Hopital rule again. Okay, so you get negative sine x over 6x. Okay, because you get 0 over 0. And next, what do you get? Can we compute limit already? Not yet, because sine 0 is 0, 6 times 0 is 0. Again, another intermediate form. Okay, so we could get minus cos x over 6. Only then you will get minus 1 over 6. Okay, good. Okay, so make sure every time when you want to use L'Hopital rule, right, write down the intermediate forms. Okay, so that we know you are using it in the right way. Okay, you cannot just try to differentiate and then compute the limit. Okay, that's wrong. Okay, let's try another different intermediate form. How about this one? Okay, let's try L'Hopital on this. So can we use L'Hopital here or not? Any intermediate form that's useful here? So if x go to infinity, please don't do substitution on infinity, but try and see what's the behavior of these functions. So if x go to infinity, e to the minus x should go to 0. And if x go to infinity, x to the inverse also go to 0. Okay. So this is a thing over 0 over 0. Okay. You want to try? I'll let you try. I'll let you try. Let you try. I think 1 minute plus you should be able to get something, or either you stuck. You try. Okay, please try. Take the time in class to do exercise. Otherwise, you go back, you do something else, you don't do anymore. Okay, what did people do? Can anyone tell me what you do? You want to try? 0, but how you compute? So how you use L'Hopital rule here? Huh?
Actually, I think you change this. That's to be
Okay, so make into some form that maybe is easier to differentiate later. Okay, but in this case, what do you get? What's the intermediate here you get? Why can you use L'Hopital? What's the intermediate form? Huh? What's the intermediate form here? Infinity over? Okay, good. So then you can use L'Hopital. And you get 1 over e to the x, and then you get 0. Anyone try differentiating e to the minus x and differentiating x to the minus 1? Anyone do that? No, me? Wow. Everyone's so brilliant. So if you differentiate e to the minus x, what do you get? If you try do L'Hopital here, what do you get? Minus e to the minus x, right? And then bottom, minus x to the minus 2, like that. Is it? Okay, is it helpful? No. And then if you keep doing it forever, you just get stuck. Correct? So this is the point of this question. Okay, if you pick the wrong way to continue, then it's not that you cannot get it, but if you just keep differentiating, then you won't get it. Okay, unless you have other method to compute. Does it make sense? Okay. If you keep doing it, I think you will like get to the e to the minus 1 to the n, maybe, or n factorial of x to the minus n, like that. You could get something like that. I think not divide by n factorial is multiplied by n factorial. Then you go crazy. Okay. So the point here is to pick some nice form for you to differentiate and then get to some function that you know the limit of. Okay. It's not that you cannot do that, but you don't have other tool to check it, then you you pretty much get screwed. Okay, any other question so far? Any question? We haven't finished examples here yet. Maybe next week we'll continue with L'Hopital rule again. Okay, if more question, please put in Moodle, message me or ask your friend. Okay, so see you next week.
话筒为正确放置。以上。